Here we are going to create a straight line in three-dimensional space by using vector equations. And this is probably something new for you guys, but it's going to be a very important thing in this lecture. Vector equations. So it's lines in 3D that we want. Some of you might ask me, why don't we just use a simple linear equations like y equal to ax plus b, like this. Y equal to ax plus b to represent a straight line in the space. Well, yes, you can use this for the straight line in the space, but it only works on 2D. What you see right here is a straight line only on two-dimensional space. Straight line only on 2D. If you use this same equation in 3D, this becomes a plane. Alright, so that is the problem here. Using the same equation becomes, well, I can just put plane in 3D. Okay, this is plane in 3D. Well, the thing is, we don't want plane in 3D, we want aligned. So this means that we need to rely on a different way, and that is vector equations. Okay, so this is the thing for today, vector equations. So let's take a look how it's done right here. We have this figure on the right hand side. I know it's kind of messy already, but please try to follow the step along with me. So we want this straight line, this black straight line of L. And we are going to find a way to represent it in three-dimensional space. Now, the first thing we are going to do is to put a point in the space right on the line, the first one. Let's call this point P0. Alright, and this point P0 has its own coordinate, and each component is x0, y0, and z0. Okay, now we put a point on the line, and the next thing we are going to do is to create another vector connecting from the origin to this point. Right? Okay, now this is the vector starting at the origin and ends at this point P0. Okay, and we are going to call this point R0. Oh, sorry, call this vector R0. So let's put this vector R0 right above point P, R0. This is a vector. Now let's find the component of this vector. And since we know the starting point and the terminal point of this vector, which is this starting point and the terminal point, we can use the coordinates to find the components of this vector. So let's find that. This vector R0 is going to be equal to components of the terminal point minus the starting point. The first component is x0 minus 0. Next component is y0 minus 0. And the last component is z0 minus 0. Since this is vector, I am supposed to put angled parentheses around them. Keep in mind that these R0 and P0 looks very similar to each other, but it's different thing. P0 right here is a point. So we have this curve parenthesis. This means a location in the space. But R0, what you see right here, this is a vector. Alright, that's why we have this angled parenthesis. Alright, so when you look at this R0, it points to P0. So sometimes we call this R0 a position vector of P0. Make a note here. R0 right here is position vector of P0, because this vector tells us where this point P0 is located in the space. Okay, so there you go. We have this first point P0 and then this vector R0. Now the next thing we are going to do is to try to move this point P0 along the line. Right? Once again, we try to move this P0 along the line. And we can do that by try to add this vector V I'm going to write this vector v right here. This vector v is going to be a vector that points in the direction of the line. Well, it's going to be the same as this vector v down here, but let's put it up here, this vector v. Alright, now that we have this vector v on the line, what happens if we add this vector r0? Take a look at this vector r0 to this vector v. If we add these two vectors, we are going to end up to a new point on the line, which is this right here. Right? R0 to P0. When you add V to that, you are going to move to this new point, and let's call this new point P. And this new point has its own coordinate, which is X, Y, and Z. Okay? Now, the next thing we are going to do is to build a position vector for this new point. Once again, position vector is going to start at the origin and ends at the point in the space. We want this. And we are going to call this vector r. Okay? So let's try to find the components of this vector r. Vector r. This vector r is the position vector of point P, because it points to this location P. Now let's find the components of this vector r. So we use the coordinate of this point P, x minus origin, which is 0. So we get x, y minus 0, we get y, and last one, z minus 0, we get z. And since this is vector, so we are supposed to put angled parentheses. Alright, so we have this, we start with this vector r0. We add vector v, and in the end we get this vector r. So let's combine these vectors into an equation. So what we get right here is that this vector r is equal to the starting of this this calculation, vector r0 plus vector v. So there you go, we have this vector equations happening in this slide. So you can put a box right here around it and call this vector equation. Okay, by using this vector equation that we just built, we successfully moved from P0, which is this point, P0, to this point P. Right? Well, we have 2 points on the line for us already, but the thing is we want every single point on this line, this L, all these points. But as of now, we only have 2 points. So we are going to have to find a way to locate other points. And this can be done by stretching and squeezing this vector v. Let's take a look at this vector v. This is the vector that leads us to this new point P. But what if this vector v is a little bit longer? If it's a little bit longer, we are going to land at a different point on the line. Imagine this green vector a little bit longer. We are going to land at this new point. If it's a little bit longer again, we are going to land at a different point. And what if it's a little bit shorter, like right here? We are going to land at a different point, a little bit closer to the original point. Alright, so the key is about this vector v. We want to stretch it, we want to squeeze it, and sometimes we want to flip it to the other side. Alright, what if this vector v is flipped to the other side? We can locate a different point on the line. So it's all about changing this geometry of this vector v. And we can do that by adding an additional parameter called t right here. Let's add t to this vector equation. This t is a coefficient, right? If t is equal to 1, we are going to land exactly at this point P in the figure. But if t is greater than 1, it's going to stretch this vector v a little bit further, right? And if t is less than 1, but still positive, this vector v is going to get squeezed, and we are going to land at a point a little bit closer. And if t is negative, we are going to land at a different side of the line. So it's all about this parameter t that is going to make this vector addition flexible. So let's take a look at the figure on the left hand side. So we are going to start at point P0, which has this position vector R0. If t is equal to 0, right? If t is equal to 0, it means that we add nothing. So we are going to stay on this point. But if t is equal to 1, maybe assume it to be right here, t equal to 1, then we land at point P that we found earlier, right? But if this t is a little bit is more than 1, we are going to land at maybe a different point right here. So it's all about this t value that can locate all the points on the line. So in the end, it's this vector equations that can be used to describe a line in three-dimensional space. So vector r is going to be equal to vector r0, which is the original vector, 1 point on the line. And then we need this vector v, which is a vector that points in the same direction of the line. And then the most important thing right here is this parameter t that is going to make v stretched or squeezed or flipped. Now let's add, I know it's a lot of things that I just told you about, so let's add the definition for each vector here. So r0 right here, vector r0, this is position vector for the original point P0. Okay, now v is a vector in the direction of the line. Vector pointing in direction of line. Okay, and then in the end we have this vector r. Alright, this is position vector of any point on the line. Position vector, any point on the line. Okay, and as you can see here, we have the flexibility of assigning different t to this equation, which means that in the end, this vector r depends on t. Depends on t. And it's quite nice, it's a little bit nicer to have this parenthesis t right here after r to tell ourselves that, hey, this r depends on t. And if we assign different t, we get something different. Okay? Now, we are going to take a look at this vector equation component by component. So let's take a look down here. What you see right here on the left hand side, this is vector r. And it has its own coordinate, its own component, x, y, and z. Okay? Now, what you see on the right hand side here is vector r0 with the components x0, y0, and z0. And then we have this vector v right here, and vector v has its own component, v1, v2, v3. The reason I wrote this is that we can look at the vector equations component by component like this. And when we look at this equation, we can separate the component from each other. First, I'm going to separate x component out of this equation. I get x equal to, the other side, I take the x component, x0, plus, now the x component of v, that is v1, t. Alright, that is the first component, x component. Second component, y equal to y0 plus t v2. That's y component. And the last component is this z equal to z0 plus tv3. So there you go. You have the separate components of this equation. And sometimes we look at this as parametric representation because we have this for the first one for x component, this second one for y component, and z component. So this is parametric equations. Right. Okay, so two different ways to look at these vector equations. One is in the vector form and the other is in parametric form. Now let's move to some example. Right. What you see right here at the top of this slide is the same as what I explained to you earlier, where we look at the vector equations component by component. So if we look at the x component, we would get this equation of x, and for y component, we get this equation of y, and same for z. When you represent these equations like this, sometimes we call it parametrization. Alright, so the keyword is right here. When you represent these three equations like this, it can be considered parametric, line or curve in the space. So what you see in the x equation, this represents the x coordinate of the points on the line. X coordinate. And this y coordinate. And the last one is z coordinate. And they are coordinates of the points on the line. Of the points on the line. And as you can see here, at different t, the coordinate would be different. Alright? So, I know that I explained a lot about this concept and it can get overwhelming, but what about we try to use it on an example, and you'll see that when it comes to applying this concept, it's not that difficult. So let's take a look at this example. What do they want here? They want vector equation. Alright, so definitely they want this vector equation r of t equal to vector r0 plus tv. They want this, the main formula for vector equation for a straight line in the space. And also they want this parametrization, which means that they want this kind of representation of this straight line. Okay, and then they want these two for the line passing through the point -2, 0, 4. So we get 1 point on the line, and we also get a vector v that is parallel to this line. So why don't we put these informations into a graph so that we can see what's going on. So let's imagine that we have this straight line. Okay, this straight line. Okay, and then we know that on this line there is a point and it's located at -2, 0, and 4. Okay, maybe right here. Let's assume this to be the first point on the line, -2, 0, and 4. Now that this is one point on the line, why don't we assign this point to be P0? Okay, now the next thing we know is the vector v, which is parallel to this line. So why don't we just put it like this? Vector v parallel to this line. And we also know the components of this vector v, and it's, well, let me write it right here. V equal to angled parenthesis of 2, 4, and -2. Oh, sorry, this is supposed to be angled. Alright, so this is all we know at the beginning. And now we need to find r of t. So let's take a look at the formula in the box. We already know v, so this is fine. It's already done. T is supposed to be a variable. We are supposed to leave it as it is, so we don't need to do anything with that. Now we need vector r0. But at this point, we only have a point in the space P0. So the first thing we are going to do here is to find this vector r0. Once again, this vector r0 represents position vector of point P2, P0, of point P0 minus 2, 0, 4. Now, position vector is a vector that starts at the origin and points to a location in space. So this vector r0 has to start at the origin. I'm going to assume that origin may be somewhere here, right? And the coordinate of that should be 0, 0, 0. This vector r has to start at this origin and points to this P0. Okay, looks good. Okay, so this is going to be vector r0, the position vector of P0. Now we are going to try to find the components of this r0. This r0 is going to be equal to, now let's find its components. Now that we know the initial point and we know the terminal point, of course we can use the coordinates to find the components of this vector. Let's start with the x component. Okay, minus 2 minus 0, so we get minus 2. Next component, 0 minus 0, I get 0. Next component, terminal minus initial, which is 4 minus 0. I get 4. So there you go, I have this vector r0. Now that we have everything, let's put them into the equations. So I have this vector of rt equal to the first vector r0 minus 2, 0, 4. Plus t is supposed to be variable, so leave it like that. And then vector v, 2, 4, minus 2. You can choose to leave it like this, or you can combine them to be in this form. The first component, minus 2 plus 2t. Next component, 0 plus 4t, so it's just 4t. And then next component, 4 minus 2t. So there you go. We have this vector equations for the straight line that passes through this point minus 2, 0, 4, and parallel to this vector 2i plus 4j and minus 2k. So this is in the form of vector equation. Vector equations of this straight line. If you want all these points, you just assign different t in there and you get different points. Now that is the vector equations. Now we have to look at the parametrization of this line. So all we need to do is to assign the to look at this vector equation component by component. So the x component would be equal to this, minus 2 plus 2t. Now for y component, that would be 4t. And for z component, easy, 4 minus 2t. And what you see right here is the parametrization of the straight line in 3D. Parametric representation of the line. Right, parametrization. Right, and that is it. So as you can see here, when it comes to calculation, is pretty straightforward, right? Now let's move to the next example. We are going to apply the same concept to this one as well. So what do we need to do here? Once again, we need to find vector equation. All right, we want to find this vector rt. And of course, the parametrization. So we need to find x equal to something, y equal to something, and z equal to something. What about I put some function in here? ft, gt, and ht. All right. So what is given to us is, well, this is the line passing through a point, and not just one point, we have 2 points, P and Q. Alright, this is a little bit different than last time. In the last example, we have 1 point and a vector, but this time we have 2 points instead. Alright, so let's go back to the main equation for the vector equation, which is r of t plus r0. Oh, sorry, r of t equal to, alright, equal to r0 plus tv. As you can see here in this formula, we need vector v, but it's not given to us. Alright, so that means we have to find this vector v. Now, I'm going to draw this p and q, alright, so that we can understand the geometry in the space. Now, we are going to have this line, this straight line, okay, and 1 point on this line would be this p, and that is located at -3, 2, and -3. And the other point is maybe right here. And I'm going to call this point Q. It's located at 1, -1, and 4. Okay, so I have 2 points on the line. So it's not a big deal when it comes to finding this R0, because all I need to do is to, well, to locate this origin somewhere, right? And this is 0, 0, 0. And I need to find the position vector to the first point on this line, and that would be P. Alright, so I'm going to assign this to be vector R0. Not hard to find, so let's do that. Position vector that points to P0. I'm going to find its component by looking at this coordinate. -3 minus 0, I get -3. Second component, 2 minus 0, I get 2. Last component, -3 minus 0. So done for the R0. But then I don't have this vector v. So what should I do? I'm going to make use of this point Q on this line. Because with this point Q, I can connect P and Q together and create this vector v. Alright, so what you see right here is vector v, and it's equal to vector PQ. So why don't we find that vector PQ? Vector PQ. Want to find the component? So I'm going to use the terminal point right here and the initial point here at P. And it's going to be terminal minus initial. So first component, terminal Q, is 1 minus the initial at P, which is -3. For second component, Y component, start with terminal, that is -1, minus the coordinate of the initial point, which is 2. And last component, 4 minus -3. So I have this vector PQ to be equal to 4 and this -3 and 7. Alright, and this is PQ, and also equal to vector V that is parallel to the straight line. Parallel to the line. Okay, now we have R0 ready. We have vector V ready. We just need to combine them. So R of t, the vector equation for this straight line would be start with the vector R0, which is -3, 2, -3, plus t. Vector V is 4 -3, 7. Let's combine them into one set of component, and that would be -3 plus 4t. -3 plus 4t. Second component, 2 minus 3t. And last component, -3 plus 7t. and we all know that this is x component, y component, and z component. So we can separate them and write them like this: x equal to the x coordinate equal to minus 3 plus 4t, y equal to 2 minus 3t, and z equal to minus 3 plus 7t. So we have two answers right here. The first one in the form of vector equations, and the second one is in the form of parametrization. Right? So here, vector equation, and what you see down here is parametrization. And you can make a note here that this represents coordinates in the space. X, Y, Z coordinates in the space, well, of the points on the line, of points on the line. Okay, so that's it. As long as you understand this one formula, what is the R0, what is V, it's in the end it's quite easy to perform the computations. Now let's move to the next one. Now that we know how to express a straight line in three-dimensional space using a vector equation, let's do some additional calculation with that. In this slide, we are going to compute distance from a point to a line. So here is the main thing for this slide: distance from point to a line. And we are talking about any point in the space to a straight line in three-dimensional space. So let's make a note here. We are talking about 3D. Okay, so let's start with the straight line in this figure. So let's assume that we have this straight line in 3D space, and we are going to perform some calculation with this line, which means that we are supposed to know its equation. And let's assume that we know its equation to be RT equal to vector R0 plus TV vector. So this is the vector equation that we learned in the last topic. So let's assume we have this information about this straight line. And then let's put a point in the space. For example, right here, this point S. Well, you can choose another point for this point S, but I need to put it right here to fit in this figure. And then with this point and this line, I want to know the distance between them. Alright? We all know that when it comes to the distance between a point and a line, it has to be the length of the path that is orthogonal between them. So the first thing I'm going to do here is to create a path between them. This path is going to be orthogonal to the line. Alright, this is the path we want, and as you can see, this makes 90 degrees to the line. Once we have this path, and if we can find the length of this path, it's going to be the distance between point and the line. So we want to find the length of this. D equal to the length of this path. Well, let's assume that we don't know this for now. I'm going to erase that. So our job here is to find what D is. Okay? Now, with the information we have right now, it's not enough to find the length of this path. So I am going to add a few more. The first one is this point P. So we are going to pick a point on the line anywhere, but I'm going to pick it right here at point P. And with this point, I can create this vector PS connecting this point P to the point S that I had earlier. So with this vector, I can call it vector PS. Alright, this looks better. This is vector PS. Now with this vector, I would like to add one more information about this figure, which is the angle that this vector makes to the line. And let's assume that angle to be theta. Alright, now that I have this vector PS, I have the line and I have the path, and you can see here we have the right triangle, and we are going to make use of that to find D. Okay, now I am going to use the trigonometry, which means that I need the length of the hypotenuse. The hypotenuse is the side that is the opposite of the right angle. I need to find the length of this vector PS. And of course, if you know the vector, you can find the length of that vector by taking the absolute value. So the length of this side would be PS absolute. And with this angle theta, I know right away that the side of this path, this green side, is going to be equal to, well, I am going to repeat again what I just erased, which is PS absolute sine theta, following the trigonometry property. D is going to be equal to the absolute value of PS sine theta, and that's why we have it written right here. So if we can find this absolute PS sine theta, we know D. Alright, so this is the main formula to find the distance between a point and a line. But it turns out that there is a small problem with this formula, which is this theta. Why is it a problem? Because usually we have the information of the line, the information of the point, but the problem is with this theta, we don't usually know the angle between the vector PS and the vector of the line, so this theta is mostly unknown from the problem. Mostly, this theta, well, I can say most often, it is unknown to us. So with this theta being unknown, we cannot use this formula directly. So what I'm going to do right here is to change this formula into another form that is easier to use. Alright, so let's take a look here. I'm going to start with the second formula for the cross product. If you can remember, if I cross product between vector PS and vector V, oh, by the way, we have this vector equation for the line, right? Which means that we are going to know this vector V for the line. So it's available for us. Now back to the cross product formula. The second one would be this absolute value of PS, absolute value of V, sine theta, times vector n hat, which is the unit vector that is orthogonal to both PS and V by using the right hand rule. But here we are not going to make use of the whole formula. We are going to take just the absolute value. So I'm going to take absolute value. Alright, now I am going to split this absolute value right here. Okay, so this n hat is going to have the length of 1. It's gonna well become 1 right here. At the end I have this absolute value of PS cross V equal to absolute value of PS, absolute value of V, sine theta. Alright, and I am going to move this absolute value of V to the other side. So in the end I have this absolute PS cross V divided by absolute of V equal to absolute value of PS equal times sine theta. Alright, at this point you can see that the right hand side of this equation is equal to absolute PS sine theta, the same as this formula for D, which means that this is going to be equal to D. If this one is kind of hard to use because of the theta being unknown, we can use this instead. And that's why we have this adjusted formula down here. the distance between a point to a straight line in 3D, you can use this formula to find that length of d. The question is, why is this formula better? Because in this formula, all we need is this vector ps, vector v. Vector v is available from the vector equation RT. So we usually have this since the beginning. And now PS can be constructed from point P, from P and S. As long as we know the point S and we pick a point on the line, we can create this PS. And D can be calculated much easier than the previous formula. Now let's try to use this formula on one example right here. Okay, now in this example we want to find the distance from this point 115 to the line right here. Okay, so let's take a look here. We have this x equal to 1 plus t, y equal to 3 minus t, and z equal to 2t. What you see right here is parametrization of the some line. So we can put a note right here that what we have right here is parametrization of line in 3D, because we have x, y, z, right? Now back to the formula that we need to use when it comes to distance between point and a straight line. That's going to be d equal to the absolute value of ps cross v divided by absolute value of v. So we need to find all these terms in order to find d. So the first thing is v. Let's try to find this vector v. This vector v is going to be the vector. V is vector in that point pointing to the same direction of the line. Vector and, well, point, okay, pointing to the same direction of line. So we are looking from this RT equal to R0 plus TV. It's going to be this. So to find V, we need the line equation in terms of vector equation. We need this form in order to find this. But what is given to us, it's represented in parametrization. As you can see here, what you see right here is x, y, z. It's not the same as this. So the first thing we are going to do is to transform the parametrization into a vector equation. So make a note here, transform parametrization to vector equation, so that we know what V is. So parametrization to vector equation, I am going to combine all the components together, x, y, and z. What you see above is for the vector r. So vector r right here, vector r is going to be the x component of what we have above, which is 1 plus t. And the second component would be y, and that is 3 minus t. And the last component would be 2t. That's for z. You can make a note right here. This is x, this is y, and this is c. And when you combine them, this becomes vector of RT. And now we want to make this vector equal to r0 plus tv. Okay, now I'm going to do the same for this line. What I'm going to do down here is to split between the terms that is just constant and the term that is associated with t. As you can see, this term at the back has the t parameter with them. So I'm going to find r first. So r right here is going to be the term that doesn't have t. And for the first component, that would be 1. So I'm going to put 1 here for r0, the first component. Next component, the term that doesn't have t, is going to be this 3. So this second component, 3. Next one, the term that doesn't have t, there is nothing. So I'm going to put 0. Alright. Now, plus, for the back term here, I'm going to take t, the common parameter, to the outside of the parenthesis. Now with t in front, I can put a vector back here. Let's take a look here. This is t with the coefficient of 1. So the coefficient here has to be 1. Now the next term here, coefficient is -1. So I put -1. And the last term, coefficient, is 2. And we can put 2 right here. Okay, so by splitting between the term with the parameter t and the term with just the constant, we end up with 2 separate vectors. The first one here is going to be r of 0. And the second one right here is going to be vector v. Okay. So you can try to multiply t in and add them together. It's going to come out to be the same. Right? Now that we know vector v, let's try to find the next term we need. Alright? This vector v is already ready for us, which is this vector v. Now we have this formula right here, and the next one we are supposed to find is ps. We are supposed to find this vector ps. Let's put it right here. We need to find this. So we need 2 points. One is point S, which we already know, 115. Another one is a point on the line. Right? Make a note here that S is point given to us. Well, I can just put 115 right here. Is 0.115. And about P, it can be any point on the line. So I can find a point on the line by using the information given to me. For example, I know that x equal to 1 plus t, y equal to 3 minus t, and z equal to 2t. What if I set t to equal to 0? I pick a point by setting t equal to 0. You can pick other t as well. So let t equal to 0, and I get this point P to be 0 goes in here, x becomes 1. 0 goes in here, y becomes 3. 0 goes in here, z becomes 0. So I have 1, 3, 0 for point P. You can pick t equal to 1 to 2, that's up to you, as long as this point is on the line. Okay, now with this point P and point S, I can find the vector PS by subtracting the components of the terminal point from the initial point. Starting with the terminal, which is 1 minus 1. 1 minus 1. Second component, S minus P, 1 minus 3. And the last component, Z component, 5 minus 0. Okay, 5 minus 0. 5 minus 0. So here I have this vector PS to be equal to 0, minus 2, and 5. Alright, now I have this vector PS ready. I have this vector V. All I need to do is to cross them together. So I'm going to find PS cross vector V. Alright, so it's going to be equal to this procedure, I, J, K. And the first component, the components for the PS should go to the next line, which is 0, minus 2, and 5. And components for V comes in here, which is 1, minus 1, and 2. Alright, and let's perform the multiplication. I'm going to cross down the first one. I get minus 4i equal to minus 4i. Cross down again, j5 and 1, I get 5j plus 5j hat, and cross again, I get k 0 minus 1, so I get 0 plus 0 k hat. Now I need to cross up and then put minus sign in front. Now cross up, 1 minus 2k, so I get minus 2k. Minus 2k hat. Alright, cross up, minus 1, 5, and I get minus 5i. And the last term is going to be equal to 0j, so that would be 0j plus 0j. Now I combined all of these terms. I get so let me see, minus 4 plus 5, so I get 1i, just I. Okay, now for j I have 5j plus 5j plus 0k and minus 2k, that's plus 2k. Alright, so what we have right here is PS. So you can present this in this form, this vector in this form, 1, 5, 2. Now what we need to do next is to find this D. Alright, and we need to find the absolute value of this. Absolute value that would be equal to square root of 1 square plus 5 square plus 2 square. So that is 25, 4, 29. So we have this square root of 30. Okay, so that is for absolute value of PS cross V. Now the next thing we need for this D is going to be the size of vector V. So V is right here. Okay, V right here, I am going to take the absolute value. So I have this absolute value of V equal to square root of each component square, 1 square plus minus 1 square, and plus 2 square. So what I have here is 4, 5, 6, square root of 6. So here D is going to be equal to absolute of PS cross V, down here square root of 30, divided by the size of the absolute value of V, which is square root of 6. So here I have square root of 5 as the final answer, equal to D. Alright, and that's how you use this formula to find the distance between a point in the space and a straight line in the space as well.